Hiya, this is a quick video on how to solve question with the lift by special request. We're looking at this. The question that I've got is this one. A woman travels in a lift and her mass is 50 kilograms. The mass of the lift is 950 kilograms, and the lift is being raised vertically by a vertical cable, so no angles there. It's attached to the top of the lift, and the string is moving upwards. Constant deceleration, and that is important, of 2 meters per second. We want to find the tension in the cable, and then finally the magnitude of the force exerted on the woman by the floor of the lift. So they're two quite different questions, these ones. And if you've been doing the connected particles one, it gives you a clue for the second one, how we want to look at this. But these lift questions contain, you need to know all 3 Newton's laws to work these. You might not feel like you're using them as maths, but you need them to understand the question. So if I were to draw this, first thing with mechanics questions, draw a diagram. It's always going to be the way. We've got our lift on a cable. Here's our lift, and we've got a person standing in the lift. So what's going on in terms of why we've drawn a picture is because we want to put on all of the forces that are going on. And for the first part, we're trying to find the tension in the cable. It's a big pointer as one of the forces. So what are the forces here? They're all the things given in the question. So we've got the weight of the lady. Now she's 50 kilograms. That's her mass. So her weight acting downwards is 50 times G. And the G is 9.8 here. Newtons. Okay, so that's her. She's got this weight. We've also got the weight of the lift, which is much bigger. They are very heavy things, lifts. The lift is 950 kilograms. So again, get that out of the way, 950 G newtons. Remember, G is about 10, so we're looking at about 500 newtons and about 9,000 newtons here. Okay, there has to be something counteracting all this, because otherwise they would just be in free fall, which you might see in the movies, but we never want to experience in a lift. So what is stopping them from falling? And it's basically the tension in here. When we come to part 2, we'll look at more of the interactions and a different Newton's law. But this is what we need to do for part A, is a bit like those connected particles questions with a car and a trailer. We want to look at the whole system, the whole object in one go. So for part A, where we're trying to find this tension, you don't actually need to look at the interplay between the woman and the lift. We can treat them like one huge object that weighs, that has a mass of 1,000 kilos altogether, and so has a combined weight. So for part A, we don't need to get too tricky, don't need to worry about there being 2 things here. We treat it like one object, and there's the tension doing its job. So the other piece of information that we're given in the question is about the deceleration. Now we are given that this lift is moving upwards with actually a changing velocity, because we're given that although it's moving upwards, it's got an acceleration, and I've put the double arrow on there to show it's acceleration rather than velocity, that is a deceleration. So the lift is still going up, but it's slowing down as it goes up. So this is a lift that is just arriving at a floor. It's gone up, picked up speed, now it's slowing down in order to stop. So it's about to reach its station. And what that means is that the velocity is changing by decreasing. So I could say that actually the acceleration, even though the velocity is working upwards, the acceleration is working downwards at 2 meters per second. So if we were going at, I don't think any lift goes this fast, but if we were going at 10 meters per second, in 1 second time we would be then still going up, but only at 8 meters per second, 6 meters per second in the next. So the velocity is decreasing. But what I'm going to do is work with upwards as being the positive direction. So it's the other thing in mechanics that's really useful is if we take a direction, say the axis, y-axis, usually we get more positive as we go up. So I'm going to take this as positive direction, and instead I'm going to put a -2 on the front of that acceleration. So it's a -2 meters per second. So that's a way of showing which way it's acting. We're not going to use the velocity because we're not that interested in it. So we've got the acceleration, we've got all the forces. And this is where Newton's laws come in. Newton's first law is just that, what would happen if these forces balanced out perfectly? So Newton's first law is that if all your forces are in equilibrium, if there's no resultant force, then what happens? You're either stationary, so you're balanced, or you continue with the same velocity. So if this was going at a constant velocity, we could happily say that these would add up to that and it would all be equal. So in equilibrium, T would be 1000 G. But it's not, because we're not in equilibrium. So Newton's first law would give us no acceleration. We're not in equilibrium. So Newton's second law is that there is a relationship between the resultant force and the acceleration, which is the only bit that looks really mathematical in Newton's laws. F equals ma. Such a lovely simple equation that actually we're going to use here. So again, I'm going to take this convention of up being positive, and I'm going to look at the forces on this lift and woman combined. So the whole object. So what I've got is this T, my unknown T, acting upwards. That's my positive. And balancing out with that, acting downwards, I've got 50G plus 950G. So total weight, I could write that one down here, 1000 G newtons. 1000 G. Okay. That's the F part. On the other side, I've got the mass times the acceleration. I've got these two masses, so it's only this bit, the 1000, don't need a G for this bit. That's their mass combined, times the acceleration, and the acceleration is -2. The deceleration is 2. That makes sense what the D bit means in deceleration. Basically told me to put a minus on in front. I like to draw arrows and things. I recommend you have an arrow as well. Okay, so what we've got, if I multiply that by 9.8, I get that. On this side, I've got minus 2000. So because I've taken up as positive, I've ended up with some minus signs in there, but that's okay. You'll see they disappear. If I add this to both sides, I get, 7800 newtons. So I'll have 9800 minus 2000. So that's my tension. Notice this is my 9800 newtons. and the tension is slightly less than the weight, which is why the resultant force is this 2,000 downwards, which is producing this deceleration. So that's part one. Don't need to worry about that it's separate the woman and the lift. Treat it all as one thing. So part two of this question is slightly different. It's about Newton's third law in the second part. So I'm gonna use the same diagram. I'm gonna get rid of this bit. Might want F equals ma later. But this time I'm really just looking at what's going on with the woman and the lift. In fact, I'm going to draw a new diagram because I recommend that's what you do as well. Here we're just looking at the person and what's going on for them, and they're on this lift floor. So I'm going to kind of get my magnifying glass out. I'm going to try and ignore all this T business, and I'm just looking at what's going on between the floor and the woman. That might seem a bit odd because this does still exist, this tension and all this stuff. But let's just see what's happening during their interaction. So it's a bit like in the car and trailer ones, when you completely cover up the car, just look at the trailer. It's a bit like that. So she's got a weight still of 50 newtons, which is actually 490 newtons. So you can change it up if it's nice numbers, like it is. So that's her weight. The only other force going on here, she's not leaning on the side, there's nothing extra going on. There's only one more force on here, and that is Newton's third law is about equal and opposite reactions. So the floor is exerting a force on her feet. Think back to when you were last in a lift, and when you start moving, you feel the movement through your feet. You might be able to see stuff moving, but you'll feel a force upwards on your feet as you accelerate. And the opposite, when in this situation we're coming up to the floor that we want and it's decelerating, and you feel, ooh, you might feel it in your stomach a little bit, that, ooh, I'm going over the falls, as the floor starts to not offer you quite so much a reaction, that force decreases and that feels a bit weird. So that's what's happening here, is that the floor is still reacting to her. If we didn't have any reaction at all, she'd be falling through the bottom of the lift. So it does have the structural integrity to put that force back in there. I'm just going to call it R because this is our unknown, our reaction, and that's what we're trying to find. So let's get rid of all this stuff which might confuse us. Just look at what's going on here. So what's her equation of motion? Or what's going on with this? We've got force diagram here, and we've got the acceleration here. So all we need to worry about here is what's going on for this mass, the woman herself. So let's see. F equals ma. We've already used all three of Newton's laws. Again, she's not in equilibrium. If she was standing still, if we were at the stop, if you would just walked into the lift and it was on the ground floor, the reaction would balance out with your weight because you're not accelerating or decelerating. Equally, if we're in constant motion, Newton's first law would say these would also be balanced. So you feel pretty normal when you're just going up at a constant speed in a lift. Say you've got a long journey, maybe going up to the 5th floor for some reason, it just trucks along. You don't feel anything weird. It's when it decelerates or accelerates that you're going to feel something weird. So what's she got? So what forces are acting? Well, I'm going to stick with my convention of going up being positive. And you can do it the other way. It'd be interesting if you want to try it with down as positive. Feel free, that will also give you the right answer. But I'm going to go with up. And what I've got working upwards is the reaction. And what I've got working downwards, so opposing that, is this 490. So that's the F bit. On the MA side, we've got her mass, and her mass is, remember, in kilos, 50 kilos. And her acceleration is -2. So again, I'm using up as positive. If you did this with the down as plus, well, we'd get 490. The whole equation would just turn negative, and we get 50 times 2. So you're welcome to work that out if you prefer. So r minus 490 equals 50 times -2, minus 100. And if I add 490 to both sides, we get that the final reaction is actually 390 newtons. So that's our end result. This is 390 newtons. Hopefully that makes sense to you, that her weight, if we compare these two, the reaction is slightly less than her weight. So remember, we decided she was in that point where it's coming up to her floor that she wants and slowing down. And so the floor feels like it's dropping away. It's not actually dropping away, but it's reducing its force on her. So that makes sense. Her weight is more than the reaction that's going on, and that's why it's decelerating. So hopefully those of you who were trying that question, that makes a bit of sense, how we focus in on parts of our force diagram. So well done. This was an extension of F equals ma. See you soon.